Welcome to the review of the kinetic molecular theory. In the kinetic molecular theory, we talked a lot about the interaction of energy and matter. So first we talked about what matter is, and you might remember I defined matter as anything that has both mass and volume. In other words, it has to resist changes to its motion and it has to take up space. So when we're talking about matter, these things are thought to be true, and this is what makes up the kinetic molecular theory. We're pretty sure that all matter is made of particles. You can call them atoms or molecules or just particles if you want to. These particles are in constant motion. They're set in motion by the Big Bang. And the motion increases with increased energy. And when particles are moving, we refer to that type of energy as heat energy, which is a form of kinetic energy, because kinetic refers to motion. So this is why it's called the kinetic molecular theory, because it's a theory about moving molecules. Since motion increases with increased energy, as a result of that, as these particles move faster, they wind up spreading apart. And this spreading apart of the particles is often referred to as thermal expansion, which is a vocabulary term that you should be aware of. It just means that usually, I'm not going to write out expansion, usually things will expand when they get hot. We saw this with the sphere and the ring. We heated that in a flame and the sphere got a little bit too big to fit through the ring. We see it when we heat gases in particular. We saw the balloon inflate over our flask as the air inside of the flask expanded. There are some exceptions to the rule, but in general, if the particles are moving faster, that means that they have more ability to spread apart. They collide with one another with more force, and that pushes them apart. And the last bit of the kinetic molecular theory is that different particles are made of different atoms, and different atoms, as we know, have different numbers of valence electrons, and all of this affects the degree to which they're attracted to each other. So if particles have a strong attraction for one another, then we say they have strong intermolecular forces, and that holds the pieces of that substance together. For example, water has very strong intermolecular forces because water, you'll remember, is covalently bonded. It's got hydrogen and oxygen atoms that are sharing electrons. The oxygen atoms are pulling those electrons towards itself, and so the hydrogen atoms are like little exposed protons. That means that the water molecule is very polar. It has a positive side and a negative side, and we see every time I run the balloon through my hair and then run that balloon next to a stream of running water, the water is pulled towards the balloon because of those strong charges on the water. Those charges also make individual water particles strongly attracted to one another, and that's what makes water so clingy. Its particles cling to each other. It has a strong intermolecular force holding it together, which is why it requires so much heat energy to boil water, and not as much heat energy to turn something like hydrogen or oxygen to a gas. Hydrogen and oxygen are both gases at room temperature, but put them together and get that polar molecule, and all of a sudden it's hard to pull them apart. So all of this affects how matter goes through the different states. So let's look at that. So here's a pretty complicated looking diagram, but it's actually very simple at its core. Just look at the blue dots for a second. Here's a sample of some substance in the solid state on the left-hand side. In the solid state, the particles are fairly close together. They have definite volume, meaning that the amount of space they take up is fixed. It's not changing. They have a definite shape as well. They hold their shape. There's two different kinds of solids. There's the crystalline type, so that solid would be made of very specific geometric patterns. The atoms would arrange in a pattern that's recognizable. But there are also amorphous solids that if you looked at it under a microscope, like let's say a piece of glass, you would see that there aren't actual crystals. The particles are really close together, but they don't have an actual pattern that they hold to. Solids are in motion. You can't see the motion of the particles, but they are vibrating in place. So the space between those individual little blue circles is actually filled with the vibration of the particles, and we can't see it because that space is a tiny space that they're vibrating in. If you add heat energy to that solid, eventually the particles will overcome that attraction they have for each other and begin to flow past one another in a rotating motion. And you can see I drew little curved arrows around my liquid. This process is referred to as melting. Oops, and I have it upside down up here. Let me move this around. Whoops, can't do it that way. Hold on. Better much, sorry about that. So You can see you're melting if you're moving to the right, you're freezing if you're going the other way. An important thing to note here is that this will happen at the exact same temperature. If, let's say that these particles were water. Water on the Celsius scale freezes at 0 degrees Celsius. It also starts to melt at 0 degrees Celsius, which is a weird thing for most students to understand. But basically what it means is, if you were to hold the temperature at exactly 0 degrees, you would see the particles going back and forth between solid and liquid very rapidly. So it would sort of melt and refreeze, and you couldn't see the particles doing that, but if you took a time-lapse image of a piece of ice held at exactly 0 degrees Celsius, it would look like it was sort of morphing and changing shape slowly over time as it melted and refroze. Clouds do the exact same thing, but they're going back and forth between the gas state and the liquid state, and as they do that, they change their shape continually as well. So after we turn to a liquid, we have definite volume. We still take up the same amount of space. No matter what you do with a liquid, you can pour it from container to container, you can even pour it out on the ground. It'll take up just as much room wherever you pour it, because the particles are attracted to each other enough that they can only get a certain distance away from one another. However, they can change their shape. They can be pushed around by the walls of a container, and so they have indefinite shape. The particles are rotating in the liquid state. Add more heat energy and you will vaporize your liquid to a gas. There's two different ways to vaporize. You can evaporate, which is the process of vaporizing just from the surface of a liquid. So when things evaporate, it's very slow. It happens below the actual boiling point, and it only happens to the molecules that are sitting on the surface of the liquid, and they have more of an ability to escape because there's nothing above them, so they're not held in place as tightly as molecules below. So evaporation takes a long time because it has to happen one layer at a time. Boiling, on the other hand, happens throughout a liquid, and you know something's boiling because you'll see bubbles form, and those bubbles are the liquid turning to a gas inside of itself and then floating up to the surface. If you cool off a gas, it will condense. We saw this happen in our fractional distillation labs with the cherry Coke, and again when you separated your sludge. The little glass bend is a place where as the liquids turn to a gas, they hit that cold glass bend and they recondense into a liquid. You can see that the particles of a gas have no definite volume and no definite shape. They will move into any container that you put them in, they'll fill it up completely, and they will take the shape of whatever that container is. And those molecules are totally free from each other. They've completely overcome their interparticle attractions or intermolecular attractions, and they move in straight lines until they hit something and then they bounce off. If you continue to heat a gas, you will turn it to a plasma, and the only difference between a gas and a plasma is that when gas particles collide with enough force, they actually break the atoms apart temporarily, so that the nucleus, the positively charged nucleus, and you can see I have sort of little pink positive signs in the middle, those positively charged nuclei lose their electrons temporarily. They get knocked off, but they're attracted back to the nucleus, so they go back home eventually. So a plasma actually has a charge to it because the atoms have become separated by these huge collisions between gas particles. As a result, when the electrons come back home, as they return to the nucleus that they were ejected from, they release a little bit of energy in the form of light, and so a plasma will give off light. Plasma is the most common form of matter in the universe. We don't think of it that way because here on Earth we don't see very many examples of plasma. Lightning is a plasma, the lights in our room are a plasma. Anytime you see light being given off, it's because there's a plasma that's been created. However, the reason that it's the most common state of matter in the universe is because if you think about all the billions of stars that are up in the sky, and they're all giving off light because they are all in the plasma state. So that's it for the kinetic molecular theory. You want to make sure that you can describe the 4 different states of matter, that you understand whether they have definite or indefinite shape and volume, what type of motion they have. You want to know the different names of the state changes. Pay attention to the one up at the top with the 2 arrows way up at the top, the little purple ones. You can go directly from a solid to a gas. That's what our dry ice did. That's called sublimation or subliming. And if you do the reverse, if a gas turns directly to a solid, that's called depositing. And you notice that when I brought the dry ice box into the classroom, it was covered with frost, and that frost actually came directly out of the air. There were water molecules as a gas in the air, and they collided with that really cold box and instantly turned from a gas to a solid. That's called depositing. Okay, see you guys in class.